All right, let's go from huge infinite stuff back to itty bitty living space. So this is just two elements, my favorite space, because I can't make a minus on here in this one. So in this space, it is a vector space. There's only two guys, two boxes. One box is this box of all evens. I'm going to put a 0 on the outside so I remember what's in the box. Because if you know me now, you know I forget things all the time. Then I'm going to take all the odd numbers and put them in the other box and call it 1. So set them all in on it. So I took the whole number line that you learned about when you're little and I put it into two boxes. So the only things in Z2 are two things, 0 and 1. The 0 box and the 1 box. And I've left these box symbols around it so you remember that it's a box. I don't think I do that with your, no, I don't define it. I can define addition. If I take two evens and add them, I get an even. 4 plus 2, even. You believe it? You can prove it now because that's one of the easiest things you can probably prove in our class. If I have two odds and I add them, what do I get? Even, but then I'm in the even box. Adding two odds gets me, adding the odd box with the odd box gets me back to the even box. So 1 plus 1 is 0. What did you learn today in foundations? 1 plus 1 is 0. And then if you do 1 and 0, you get 1s. Odd plus even, you get an odd. So I can make what we call an addition table. There's only a few combinations in here. No minus signs, no negatives. Isn't that nice? I can also define scalar multiplication, but this time my scalars are not going to come from the reals. My scalars are going to come from Z2 itself. So I'm just going to put all the possible scalars on all the possible vectors, and I can actually, one by one, do it. So with this, on your homework, I ask you to exhaustively, it is exhausting actually, that's why I use that word. You just go through all the different cases to show that addition's commutative. All those different 7 different properties, you can actually like write them all out.
Would something like this require proofs for each one? Like an odd times or an odd times?
No. You can, no, I gave you this, so you can use
this.
This
is given.
This is the addition table. I have to define those two things before I can define what it's going to be. Now that this is defined, you'd use that table and say, look, all combinations satisfies property 1. All combinations satisfy property 2. So you actually exhaustively list it all out, which you can here because there's only 2 things. So Z2 is a vector space over the field Z2. And that you'll use Z2. Actually, I think you use Z2. Maybe use Z. I think you use Z2 in cryptography. You'll use that. So you use this thing.
So can you since Z2 is pretty easy to work with, performing a lot of operations under Z2, can you make things in Z2 if it's whatever's convenient for whatever problem you're solving? For example, numbers divisible by 3 is 0, and numbers not divisible by 3 is 1.
That would be Z3. So if you look at, you can also think of this as remainders, right? So if you have numbers that you're considering divisible by 3, that would be Z3, because the possible remainders are 0, 1, and 2. So you can repackage up the boxes so it's divisible by 3 perfectly, that's one box. Divisible by 3 with a remainder of 1, that's the next box. And so you can put up a Z3 too. And when those things are prime, you have certain properties that are nice. They're fields. If they're not prime, they're not fields.
So you can take divisibility and define it as a set then?
That's what we just did. Okay. That is exactly what we just did. Right? Those things that are perfectly divisible by 2 go in the 0 box. Those things that have a remainder of 1 go in the 1 box. That's exactly what this is. So you're looking at remainders. All right. We have a little bit to touch up on your in-class assignment from yesterday, so why don't we do that? You don't want me to give you more. I probably twisted your mind today with these examples.